So hey, good morning, everybody. It is great to have you here. It's a great group and a great day. So real quick, do a couple introductions. First is Stephanie Smith. Stephanie is right here in the front row. Stephanie is Regional Agronomy Manager for 360. She covers northern Indiana, Michigan, and all parts east. Stephanie has a very broad and deep background. She has spent years with both Monsanto and Tech Development Group and DuPont Pioneer in their agronomy group as well, and is one of the best agronomists that you'll find. So we're really fortunate to have her, and she's going to jump in the talk and join us here in a little bit. We can go over some real world examples. And then my name's Jim Schwartz. I'm the Regional Agronomy Manager for Southern Indiana and Ohio, and contrary to what Greg said, I know just a little bit about nitrogen, and after this year, I know less than I thought I knew. So I live in Noblesville, Indiana. I will share with you, it was a really interesting year in Noblesville, which is just north of Indianapolis. It only rained twice, really, this year in Noblesville. Believe it or not, 2 times. Once was for about 47 days, and then the second time was for about 20 days. But other than that, we were bone dry this year. So it was wet. Like Greg said, it's tough crops over that part of the world. But I've been in agriculture for about 30 years, mostly as an agronomist or an agronomy manager. So my topic today is really about nutrition. We're going to talk about specifically sulfur in a little bit and how that ties into nitrogen and nutrition in the corn plant. And then also Greg asked us to talk about nitrification inhibitors to get a little better clarity about it. Now before I do, I want to tell you about my sons. They're actually here today. This is on your right is my oldest. He goes to a small Christian college over in Ohio called Cedarville. He wants to be a college professor. The one on your left is my youngest. He wants to be either a plant breeder or an agronomist. But I want to tell you a story. And it's about my sons. When my brother got married, they were the ring bearer. The one on the right, the youngest one, was the ring bearer for the ceremony. And I was a groomsman, and I'm standing there, and that little guy on the right, he's 2 years old at the time, and as he's coming down the aisle to do the ring bearer, bring the ring in, he starts walking down the aisle and he goes, "Ah!" And then he goes the other side and he goes, "Ah!" And he does this all the way down the aisle. Now I'm thinking, okay, I've bred an absolutely insane young man. I have no idea. I give him the death stare and he looks at me. Well, what he thought we said was, "We want you to be the ring bearer," okay? Now, that is a true story. He's here. You can ask him. Now, here's the worst part of it. Up until about 3 years ago, I didn't even know that. I just thought he was crazy, okay? But the truth of the matter is, he thought we asked him to be a ring bearer for the wedding, not the ring bearer. That's a true story. And my point is, we didn't communicate very well, all right? So make sure as we go through this, if you have questions or comments, stop me, ask me. I don't want you to think it's a ring bearer, okay? So why are we going to talk about stabilizers and nitrogen? Why are we going to talk about sulfur? Well, things are changing, right? This chart shows you the change in heavy precipitation in the last 50 years. Folks, that's a trend line, right? That we are getting more and more heavy rainfall events every year. If you look, here's another look at it in a different way. In the upper Midwest, all right, the upper Midwest has seen a 50%, we have seen a 50% increase in 4-inch rainfalls across that upper Midwest in the last 100 years. That's your last 50-year look. This is your last 100-year look. Here's another chart from Iowa State Climatology. If you look, they took the blue triangles are 1893 to 1980. The red squares are 1980 to current. They took all those years, all the weather. One axis is, if you look at the bottom axis, that's May-June precipitation, less more. Then the next axis is July-August precipitation, less more. So if you're in the upper right-hand quadrant, that means you're really wet. If you're in the lower left, that means you're really dry, okay? Here's the interesting thing. They bunched all those years together, and they found kind of what looked like would be the cluster of normal. But look where the last 5 years fall in that chart. If you look down in the lower left, you see 2012. Then look where you see 2010, 2011, 2013, 2014, and where you think 2015 is going to fall. Upper right? We are seeing more and more years where we have heavy precipitation events, and this year was no different. So if that's the case, if that's the new reality we live in, we need to start thinking about our nitrogen programs, how we protect the nitrogen in our soil and make it available to our plants so it's there later in the year. The other thing that's changing is we think hybrids are changing as well. This is a study that I pulled this data out of a Pioneer agronomy book. It's right in the front couple of pages. There's 2 different studies here. The green one is from Purdue University. The yellow one is from Iowa State. And here's what they're finding. As we make these hybrids healthier, as we keep them alive longer with traits, they're using more nitrogen later in the year. If you look at that chart that says post-flowering N uptake, and then look at the column, and then look all the way over to the right. The interesting thing is, what we're finding is modern hybrids, because we keep them alive longer, because they have these traits that are keeping them healthier longer, they're using nitrogen later in the year, more of it later in the year than they ever have before. So we have more rainfall, and we need more in later. That means we've got to do things to start protecting the nitrogen we have to make it available later in the year from a plant health perspective. This is a chart, I saw this last summer for the first time. Dr. Jerry Hatfield, he's in our CS, he's an adjunct at Iowa State. And it was data he'd worked on. You can see 3 different boxes over 3 different years. Don't worry about all the little numbers and stuff. Here's the bottom line. What that's showing is a correlation between yield and plant health. And what you can see there is the longer we keep these hybrids alive, and this is pretty intuitive, right? The higher the yields we're going to experience. So our charge in a year where in an environment where we're getting more heavy rainfall and hybrids are using nutrients later in the year is to keep them alive longer to drive those yield levels higher and higher. So before we talk about keeping nitrogen in the field longer and later, I think it's important to talk about how we lose it, right? There are really 3 main ways. One is volatilization, all right? That deals with the urea molecule. We'll talk about that. Then there's one called leaching, and there's one called denitrification. Leaching and denitrification deal with the nitrate molecule, right? And then the 4th way really is surface displacement, which we'll touch on that very, very briefly, but that's some of these 4-inch rainfalls, physically moving that off the surface of the soil. But we're going to spend a little bit of time talking about those first 3 mainly. So how do we prevent those losses? Well, one is we can prevent, and I'm going to go into this in just a minute, we can prevent nitrification, and I'll show you what that means, and we can prevent urea hydrolysis, and then there's also ways like polymer coating, sulfur coating, some other ways to prevent the loss. So if I'm going to talk about slowing or stopping nitrification, let's examine it real quick. So nitrification deals with the conversion of the ammonium molecule over to nitrite and then to nitrate, all right? If you look over on the right, you see the NO3 negative molecule, that's where bad things start happening. 2 things happen with that molecule. Number 1, it's negatively charged. Your soil's negatively charged. It can leach through your soil profile. It's not held by the soil. Secondly, that molecule on the right is the one that gets denitrified and converted into nitrous oxide, dinitrous oxide, or pure nitrogen gas in waterlogged conditions. So bad things happen when we get over on the right-hand side of that equation. All right, so think about 28% has urea, ammonium, nitrate, and I'll talk about urea in a minute. So 75% of that 28% goes through this process, all right? The other 25% starts over on the right-hand side, and then all your anhydrous goes through this process. Here's the bottom line. I'm not going to spend a lot of time. We did this last year. We talked at depth about this. But if you look when it goes from the ammonium molecule, that's NH4, has a positive charge, it's held to the soil. It is converted to nitrite by a bacteria called Nitrosomonas. All right, the Nitrosomonas are a bacteria. This is a biological process, so heat, temperature, oxygen, pH all impact the speed of this conversion process. But those bacteria build up and they convert that ammonium over to nitrite and then to nitrate. Now that's not necessarily a bad thing because the plant takes up the majority of its nitrogen in the nitrate molecule because it's mobile and it moves through the plant and soil water. But what we try to do with nitrification inhibitors is kill off those bacteria, and that's what they do, okay? The nitrification inhibitors are targeted for that ammonium molecule, and the goal is to kill Nitrosomonas bacteria. And what it does is it gives you 10 to 14 days before those bacteria have to repopulate your soil to build back up and start driving this process. Because the longer we keep it in the ammonium form, it's held to the soil, all right, and it extends the life of that nitrogen, especially if you think about all the heavy, heavy rainfalls we've had, right? That nitrate molecule washes out. The ammonium molecule does not. It's positively charged. So that's the goal, is to keep it there. They kill the Nitrosomonas bacteria. You've heard of things like Inserve, Instinct. Nitropyrin is the active ingredient. They work. They're proven technologies. They do what they say they will do, and they're very effective, all right? So the other thing then we talked about was urea hydrolysis, all right? If you look, this is over on your left is the urea molecule, all right? When you add the urea molecule to your soil, to the surface, or inject it to the soil, it grabs hydrogen, it combines with water, and then it grabs hydrogen and it creates, over on the right, what is that? That's ammonia gas, right? So we have to get that ammonia to grab a hydrogen from water to become ammonium, which if you think about it, that's really what you're seeing over on the left here, right? It's the same thing. But you want it to grab the water from ammonium to become, from water to become ammonia, so it is bound to the soil. Otherwise, if it lays on top of the surface, what happens to that NH3? What is that? It's gas, right? And off it goes into the atmosphere. Now, this process is driven by an enzyme called urease, okay? Urease, this process is driven much quicker at higher pHs. So think about that. If you're a no-tiller and you spread lime on top, if you have heavy residue on the surface and you prevent that urea from getting in contact with the soil, if you have high temperatures, all right, high moisture on the surface, all those things will drive this process faster. In fact, as you look, I put a number up there and it's relative, but you can lose, it starts after a couple days being on the surface, up to 3% per day of the urea portion of your 28, all right, which is 50% of that portion that you don't get it down into the soil. You need about 2/10 in bare soil, about 5/10, 4/10 of an inch in heavy residue soil to get that molecule in contact with the soil so it becomes ammonium and is held by the soil. So what urease inhibitors do, guess what? They kill that enzyme, they stop that process from going on, and it gives you time to do what? Really, the whole goal of urease inhibitors is to give you an extra week to 10 days to get a rainfall, okay, to move that nitrogen into the soil to begin the process then, really to begin that process, right? So again, real quick, nitrification inhibitors kill nitrosomonas bacteria. The goal is to keep that in the ammonium form. Urease inhibitors kill that urease enzyme, and the goal there is to give you an extra window to get a rainfall to get that urea down into the soil, okay, to prevent it from gassing off. The urease inhibitors are really, again, targeted for urea, 28, 34%. They are proven and effective. There's a new one on the market called Limus from BASF. Agritane is a common one. There's others. There are also a lot of private label products as well that have a similar active ingredient. There's also sulfur coating. So if you think about what I talked about when we discussed urea hydrolysis, I said pH, right? pH, higher pHs drive that process quicker. Well, why would sulfur coating impact urea hydrolysis? Because as it wears off, it becomes a weak acid and creates a low pH zone around that urea granule, right, the prill, and it slows that hydrolysis process down. Here's what I would tell you. It does, I mean, it works, but it's not nearly as effective necessarily as like the urease inhibitors like an Agritane or a Limus, okay? It can work, but it's not as effective as those other products, okay? There are some products out there that do both, that will inhibit the urea hydrolysis, and they will inhibit nitrification, okay? You know them, you've probably heard of Agritane Plus and Super U. There's also, it's Instinct 2, right? I think it's the new product, Instinct 2, there, right? And they're targeted, again, to stop both in 28% urea in the real world out there. So there's also polymer coating. You've heard of ESN, okay? What it does, basically coats that molecule, and it has to weather with time, really it's heat, time, and temperature. No, moisture and temperature, okay, over time. And moisture impacts it more, but the goal is basically as that polymer wears off, it starts allowing the nitrogen in there to be available to go through those processes we just talked about, okay? They work, okay? They do what they say. I would tell you, some folks, actually some ag retail folks will blend coated and non-coated urea together because they're trying to balance out having some nitrogen available right away, having some nitrogen slow release in your crops, okay? The only issue I would share with you is you can see surface displacement. If that granule is laying on top and you have heavy, heavy rainfalls and it sits there a long, long time, that can be an issue, but it's not as big a deal, okay? There's also, you heard of Nitrisphere. Basically, it's a polymer, and for lack of a better term, a biological, but it goes after both, okay? It goes after urea hydrolysis and nitrification, and it's fairly effective. Not been around as long as, say, some of the standard products that we've seen on the market, but they do what they work, they do what they say. There's also a new technology called competitive cation products. I guess I would say I need to learn more about them yet before we talk about how effective they can or will be. I went through that really quick, but again, let's think about we lose nitrogen to volatilization, urea hydrolysis, right? That's how it happens, and then nitrification. But now let's talk about the real world. I want to have Stephanie come up and talk to you and just walk through some scenarios to say, when should I use? Because if you think about it, what product you use depends on the nitrogen source you use, the time you're going to put it on, okay, and the environment in which you're going to put it on. So Stephanie's going to come up and share with you kind of some real world examples to have that conversation about what and when you should use it.
Great, thank you, Jim. Yeah, so did a great job laying out the basis of knowledge here, okay? But we're a farmer in Northeast Indiana, okay? We've got an active growing crop. We got to figure out, nitrogen changes by the day, even by the hour. So let's put ourselves into some real world situations here and think about what is best for our current situation. Obviously, we can't predict a month into the future, but today, okay, we're sitting with our side dress rig right in front of the field. What do we do and how do we handle that nitrogen? And for all of these different scenarios, okay, if you leave here without this graph imprinted in your mind, okay, we haven't done our job here. Okay, this is the uptake curve of nitrogen, when that crop actually needs the pounds out there. So let's take a look. 50% after tassel, okay, keep that in mind. So this first scenario, okay, we're at V7 to V8 corn, and you plan to apply 28% nitrogen here, and the forecast has no rain. Okay, think about what a V7 to V8 cornfield looks like. Okay, we're about at knee high, a little bit more. Okay, there's no rain in the future. We don't have canopy closure. We're still getting those light rays to hit our soil surface. What should we do here? Is it potentially that we can lose nitrogen? This means yes, this means no. Yes, we have the ability here to lose nitrogen, okay? Where are we going to lose it? Are we going to lose it down through the soil profile, through leaching, or are we going to lose it up into the atmosphere? Up into the atmosphere, right? Okay, we're going to volatilize it. Okay, if there's no rain forecasted here at V7 to V8 and we drop that nitrogen down the middle of the row, okay, let's just pretend we're using straight drops, you better stabilize it, okay? You need a urease inhibitor, okay? Let's pretend that we use wide drop in this scenario. We're still directing it under that leaf closure, okay? We still don't have 100% canopy closure here, and we still don't have 100% forecast of rain for stem flow for incorporation. Do we use a stabilizer? My suggestion is yes. Yep. Okay? So, again, why? Because, okay, we're sitting there when we haven't even used 25% of our total nitrogen in that crop yet. Okay, we still have 75% of nitrogen up to risk. So let's go ahead and think about it. We kind of tell the joke internally where let's pretend I have a target and I'm at a shooting range and I'm trying to hit a target at the end of this tent. Okay? I can shoot a little bit, but if I am closer to the end of the tent, I can probably hit that target better than all the way back. Consider my distance time in your growing season. Okay, the closer we get to making that application, when that crop needs it, we're going to be more accurate with the amount of nitrogen we're putting out there. Okay? Let's think about a different scenario. We're here at V4 corn. Okay, this is traditionally what we're used to when we think about side dressing, right? Okay, at V4 corn, that crop has not even used 10% of its total nitrogen. Okay, let's pretend we're using a coulter. Do we stabilize this? For me, yeah. Okay, to me, it truly doesn't matter whether I have dry or wet conditions coming up because I know the amount of nitrogen my plant needs as we progress throughout the season. So whether it's wide drop here, we don't have hardly any canopy, we have zero canopy closure. Okay, we're still leaving a lot. So whether we wide drop it, volatilization, stabilize it. If we put it in the ground, we stabilize it. Okay, again, If you don't have this imprinted by the time you leave, okay, this is what we're going for. Understand when that crop needs that nitrogen. Okay, what about this field? We're almost here at shoulder tall corn, and we've got an irrigation pivot out there. What does that cornfield look like at shoulder tall corn? We got pretty decent canopy closure, right? We should be pretty darn close. Okay, we also have a pivot. We still need a lot of our percentage of nitrogen left, but do we stabilize this? In my perspective, most of the time, no. Okay, I have canopy closure. If it turns out to be dry, I can turn on my pivot. When I turn on my pivot, I can probably put some more nitrogen on there. So for me, in this instance, I don't stabilize it. Jim, would you agree with that?
Yeah.
Okay, obviously, different agronomists are going to have different answers, but in this scenario, we have water, we have canopy closure. I don't stabilize this field. Again, even though we're not quite to our total percentage of nitrogen necessary to finish out that crop, I think we have other agronomic factors that are going to weigh in our favor to hold on to that nitrogen. Okay, what about this field at V16? So right before tassel, okay, you're out there with your Hagie or your Miller, and you're putting on Y-drop. Do you stabilize it? See a lot of head shakes. Again, that means no, so good job. No, I don't think we stabilize this field, okay? We have canopy closure. We're right at that 50% threshold, okay? If we're applying 28%, we still need to convert 2/3 of the ammonium into nitrate form when we use 28%. So that conversion process buys us 4 weeks, which means probably at this time we don't need a stabilizer. But Jim, this was your field, right?
Nothing you can do about that. Yeah. Any sheep farmers in here? Okay, we call those range maggots where I come from, so I just had to check. So now there's probably a sheep farmer that didn't raise his hand. I'm sorry. So anyhow, so hey, now I'm going to switch gears and talk to you about sulfur. I have a pocket full on my phone of sulfur deficiency pictures. I cover, again, Indiana and Ohio, and I can tell you I have taken picture after picture after picture of sulfur deficiencies this year. Why? Why in the world are we seeing it? Well, there's a couple reasons. Number one, we're increasing our yields, so we're removing more sulfur. All right. Number two, we're cleaning our stacks. I'm not opposed to clean air. I'm happy about it, but there's some consequences we have to think about. Also, a lot of the newer pesticides we're using, by pesticides, I'm talking about herbicides, insecticides especially, they don't have sulfur in them. Some of the old ones used to. So I figured we might as well blame something else on glyphosate, right? There's no sulfur in glyphosate, all right? And also, as we've moved towards more conservation tillage, we've immobilized sulfur in our systems, and I'll talk a little bit about that. This is the picture. I took this in Columbus, Indiana. This is a coarse textured soil. It's a sandier type soil, and it was cool this spring. And I saw lots of fields like this in Indiana, okay? This is a really interesting shot, okay? This is a government publication I pulled this out of from Purdue. It shows 1989 versus 2009, and basically that shows the deposition of sulfur in the atmosphere from coal plants, right? We have cleaned up our air. Now that deep red is greater than 10 pounds of sulfur that gets into our soil from sulfur. We've cleaned up our air. But for our crops, that comes with a price, okay? Now, it takes, to graze about a 200 bushel corn crop, all right, it takes around 30 pounds of sulfur. 45 pounds if it's 300 bushel corn. That's how much sulfur is needed. But and we'll talk a little bit more about the timing in a second, but let's do some quick math. If you think about it, okay, a 200 bushel corn crop needs 30 pounds of sulfur. You mineralize sulfur from your organic matter, okay? Again, we'll hit on that in a second. For every percent organic matter in your soil, you should be able to mineralize around 3 to 5 pounds of sulfur. That's how you get sulfur to your crop, mineralizing organic matter, all right? So if I have 3% organic matter soil times 5 pounds, that's 15 pounds. A 200 bushel corn crop needs 30. There's a gap there. Now, when I was a kid, we always used to say, we can get 10 to 20 pounds in the soil from deposition through rainfall. You saw that map. It doesn't exist anymore. And so we've started to build these gaps in our sulfur availability because we have higher yield. We don't have it in the rainfall, okay? And a lot of the insecticides and fungicides and herbicides we use don't have sulfur in them anymore. So we're starting to see this gap develop in our soils. So sulfur comes to the plant in the sulfate ion. If you see that as a double negative valency, that means your soil's negatively charged, sulfur's negatively charged. It is not held in your soil. Think about it like nitrate. It moves very rapidly. It's very mobile in your soil, all right? It's just like, if you think about it, think very much like you do the nitrate molecule. It remains in soil solution and gets to the plant in the water, just like nitrates do. Again, it's mineralization of organic matter. When you think about mineralization, I've got a slide in a second, all right? What does it take to mineralize organic matter? Heat, right? Moisture, aeration, bacteria to break that residue down. That's how sulfur gets into the soil solution to feed your crop, okay? And as I mentioned, each percent organic matter supplies 3 to 5 pounds for your plant. Those are the things required to mineralize that residue, to mineralize it, and make that sulfate ion available to your corn plant. I'm not going to spend a lot of time, but I thought this was interesting. The sulfur cycle looks a lot like the nitrate cycle, the nitrogen cycle. If you go back to school, it looks a lot. The blue is how it gets to us. The green is the form, and then the orange is kind of what happens to it. What can we do? Well, if you look, here's what I think is interesting. The orange is, you can see there's plant uptake, there's leaching, right? You see leaching there. And then also you see volatilization, right? See that over on the right-hand side? We'll talk about that in a second, and runoff and erosion, okay? We can lose sulfur a lot like we do nitrogen, okay? Here's what it looks like. Here's what sulfur does in a waterlogged soil, interestingly enough. We talk about volatilization of nitrogen a lot. Sulfur can also volatilize into a hydrogen sulfide gas. If you've stood in a wet field for a while and you're standing there and you get that smell like rotten eggs, okay? A lot of time, this is what you're smelling, okay? But again, the consequence is, think about, to me, I think we're walking some really fine lines as it relates to sulfur in our soils. And if we start having these waterlogged soils and we start gassing off sulfur, it's another penalty that's really has a big impact on what we do. Okay, sulfur, you know it. It's, you know, we talk about the primary nitrogen, potassium, and phosphorus. Whew, boy. Then the secondary is calcium, magnesium, sulfur, okay? It is a secondary, it's not a micro, it's a secondary nutrient, all right? It can be absorbed as sulfur dioxide through the pores, the stomas, okay, but that's a low percentage. It mostly comes through the sulfate ion. Here's what I really want you to take home from this, those last two bullets. Sulfur is very important in chlorophyll formation, okay? Sulfur and nitrogen are very, very intermingled in the plant. Their ratios are very important, but sulfur is very important in chlorophyll formation. That's why when we see sulfur deficiencies, what's the color we see? Light green. We see that light green, okay? The other thing I think is really interesting, sulfur is a little different than a lot of nutrients in that more sulfur is taken up later in the year than most other nutrients. 52% of sulfur is taken up after R1. So think about that for a minute. It's very mobile, and it's taken up late in the year. So what do we think, as we start thinking about plant health, we think about sulfur being very important in chlorophyll formation. We've got to make sure we're providing sulfur late in the year to that plant to keep it healthy, to help with chlorophyll formation, okay? The other thing I would tell you, and this is where that ratio, we talked about the relationship between nitrogen and sulfur is very important. Sulfur is very important in the formation of nitrate reductase, okay? Interestingly enough, your corn plant takes up nitrates. Once it does, it has to convert it to ammonium in the plant to utilize it and break it down. So what happens? That's done with an enzyme called nitrate reductase, okay? And this is where the sulfur-nitrogen relationship comes in. Sulfur is important in forming nitrate reductase to convert that in the plant. Now, what we're telling you this morning, what Greg talked to you about, is we want to feed that plant a lot of nitrogen late in the year, which we do. But I also just showed you sulfur is taken up late in the year. That's that close relationship because you have to have sulfur in that plant to convert that nitrogen to a usable form via nitrate reductase. So I guess what I'm telling you is if we're going to keep these plants healthy late in the year, we need to start thinking a little bit differently about when we put on our sulfur because it's mobile and it's used late and how we apply it. The other thing about nitrate reductase, which I think is kind of an interesting point, is that in dark conditions, under stress, okay, nitrate reductase drops. The production in the plant drops. Well, think about when Greg was showing you 50,000 plants in twin 20s. What did he show you in the canopy? It's dark, right? So nitrate reductase drops in those conditions, okay? So if we have sulfur deficiencies, it's a double whammy, Okay, so as we start pushing our pops and narrowing our rows, sulfur becomes even more important. Here's the thing I'll tell you, there's lots of sulfur fertilizers, but the thing I want you to understand about elemental sulfur, it's fine, it works, it does what it says, but elemental sulfur has to be broken down over time. The corn plant takes up sulfate, all right? Elemental sulfur has to be converted to that sulfate form over time, so if you're going to use it, you can't use it late in the year because it has to be broken down. The other thing I would tell you is, as you think about sulfur and its conversion, elemental sulfur and its conversion, there is a bacteria that does that in the soil. Interestingly enough, and this probably makes sense to you, it's more common in lower pH soils, that bacteria, than it is in high pH or alkaline soils. So sometimes we see some erratic responses to elemental sulfur applications, and that could be why. That could be why, because the conversion could be erratic as well. I'm just going to show you, I'm coming down the home stretch here. I thought this was really interesting. You can see the dates in 2006, 7, and 8. Iowa State did a study on sulfur. And what they did the first year in 2006, they did 6 sites, I think it is, right? 5 of 6 sites. They saw a significant response. The response was, 38 bushel. The other location, the 6th location, they saw an 8 bushel response, but that wasn't statistically significant. That surprised them. So in 07 and 08, they took it more locations, okay? They expanded the number of research locations, and I thought the data is really, really interesting. Here's what I would say. Look at where it says broken out by soil type, and I think this is really interesting. We talked about how sulfur gets into the plant. It's mineralization of organic matter, right? Look at the coarse textured soils. This should make perfect sense. The response on the coarse textured soils was much higher than the fine textured soil. Still a good response, but that's using gypsum that had to be mineralized over time. Here's what I'm saying, okay, as we think about it. There are fields, this field, other fields that have coarser textured soils, lower organic matter. I think we really need to be thinking about how do we get sulfur into the plant to help feed that plant and keep it alive. So let's bring it all home. S deficiencies are more common. Sulfur is highly leachable. It's mobile in the soil. Most soils typically cannot provide enough. Some can, but not many. Can provide enough through mineralization, so we have to supplement that. In a year when you have like this year, where we had cold, wet, low oxygen soils, we didn't mineralize much as well. Okay, so that was a double whammy. And over half of the sulfur is taken up after R1. And there's a strong relationship between nitrogen and sulfur. Okay, I'm not going to take you through biology class, but here's why I want to bring this all home. That is photosynthesis in a corn plant. And you remember I talked about nitrate reductase, okay? Converting that nitrogen. Just here's what I want you to understand. The green thing there, that's chloroplast, right? That's chlorophyll. Guess what one of the components of chlorophyll is? Nitrogen. You see all those enzymes up there, NAD, ADP, ATP, and NADPH? Guess what they have in their construct? Nitrogen. Nitrogen is part of their constructs. You see that enzyme up there called RUBP? That is the most common protein in a plant. Okay? It's actually believed that when corn plants start to get low on nitrogen, they pull nitrogen from RUBP. Okay? It's called Rubisco. I'm not trying to give you a science lesson, but here's what I want you to understand. If we run short of nitrogen and we run short of sulfur, okay, we start getting penalties because look what's coming out the other end of that cell, sugars, right? And if that plant starts running low on sugars, it's going to go get them. These modern hybrids are programmed to yield. That's what they do. That's what they want to do. So they go get it from somewhere, okay? And here's where they get it. Aaron Galt, you sent me these pictures this week, right? Look at the difference. If you look at the top versus the bottom, the stalk cavitation, what do you think's happening in these fields? You're seeing, right? They're robbing Peter to pay Paul. That's the bottom, bottom 3 nodes, inner nodes of that plant. And you can see as it starts running out of nitrogen, and I would contend in a lot of cases where we're running low on sulfur as well, it's a double whammy. And these plants they're going to get the nitrogen and they're going to get the sugars to fill the air because that's what they're programmed to do. But as a result, you're going to deal with it later. I would strongly encourage you this year to go out and start looking at some of your fields, start splitting stalks and see what you see, okay? Because I think this year with all the rainfall, with the higher demand late, we talked about, I think there could be some issues. Okay, wrap it up. Jordan Spieth, he's the #1 ranked player in PGA, right? Jordan Spieth has like a 68.8 stroke average. He earned $9+ million this year, won 4 major tournaments, okay? Sergio Garcia is ranked 33rd. PGA. He has no major victories, all right? He's 0.8 of a stroke behind, on average, behind Jordan Spieth. He's won about $2 million this year. Webb Simpson's ranked 53rd, all right? Webb averages a stroke and a half more than Jordan Spieth. He's won about $1.5 million bucks, okay? I guess my point is today, as you go through these sessions and you listen, figure out a way to improve your score by 1 stroke. It doesn't take a much. That's the fine lines. And maybe the fine line in your field is sulfur. Maybe that's the stroke you can pick up, okay? But be thinking about these fine lines as you can gain a stroke and really increase your bottom line. I love this quote from Abraham Lincoln. He gave this during his second annual message to Congress. If you know, that was kind of a tough time in our nation. And I loved what he said. He said, "The dogmas of the quiet past are inadequate to the stormy present. The occasion is piled high with difficulty, and we must rise with the occasion." Think about agriculture today and what we're doing, all right? As our case is new, so we must think anew and act anew. And I would contend, as we think about agriculture today, right, it's piled high with adversity. We have to deal with these things. The world is changing. Hybrids are changing. More rainfall. And we've got to think new and act new to start addressing it as we move on. Okay. Whew. Sorry. Any quick questions before we move you on? Sir? The question was, what do we mean by elemental sulfur? So you can, like sulfur, you can apply straight sulfur. It's 100% sulfur. Or like, for instance, in gypsum, there are products that are simply, like, for instance, potassium thiosulfate. That is SO4, and it's double negatively charged. So it's available to be taken up right away. Elemental sulfur would just be S, like sulfur, and it's available in gypsum. It's available as an element. You can buy it, just pure. And then that has to be converted over to sulfurous acid and then sulfate to be available for the plant to be taken up. Does that make sense?
Like a granule of sulfur put on the fall with your P&K, is that going to work?
Yeah, it's a great question. So he said elemental sulfur that is put on in the fall, that gets converted, can that be available next spring? And I would say it can. Think about it just like you do the nitrate molecule, because it has to be mineralized, has to go through that process, right? It depends a little bit on the pH of the soil, but it can be. The only issue is, let's say you put it on in the fall and it's 80 degrees, right? And we start converting that to sulfate, just like the nitrate molecule, right? If you have heavy rainfalls in the spring, June, okay, you can leach that out. You can also volatilize that off. But yes, here's what I guess the take home with elemental sulfur is, don't put it on mid-season, right? Because it takes longer to convert that to the sulfate ion to make it available. I think spring it can work, fall it can work, but it kind of depends on the weather and the environmental conditions and your soil type as well. Great question.
Here you go.
Go ahead and
Here you go.
that's the.
What type of sulfur
What
is
type
in
of
manure?
sulfur is in manure? There's elemental sulfur, and it has to be mineralized. Again, think about it will get mineralized over the course of the year, but that's and there can be sulfates in there as well. There can be hydrogen sulfide. There's a lot of hydrogen sulfide actually in manure as well, but there's a lot of elemental has to be converted as well. Great question. Anything else? Good stuff. Okay. Anything, Stephanie? Anything we missed or failed to cover? Any other questions?